In this video, we're going to learn how to count, right? Yes, you heard me right. We're going to learn how to count. It might seem like a strange thing to say, but one of the most difficult things to do in mathematics is to actually count. And I don't mean count like 1, 2, 3, but count in the sense of enumerating the number of ways a certain thing can happen, right? So it's not just, okay, can you count from 1 to a million? That's tedious, but it's easy to do. But trying to figure out how many ways something can happen is actually a pretty, it can be very, very challenging, right? So what we're going to present are a few counting techniques that will make that task a little bit easier, right? And the first, there's a principle, and I thought about giving like a proof to this, but then when I thought about it, I was like, well, let me focus on like what the principle is actually saying, and then doing a few examples, and not necessarily going through a rigorous proof, right? And so this is sometimes referred to as the fundamental counting principle, right? We've come across another fundamental result from calculus, which you guys should know by heart. But here is the fundamental principle of counting, and this is what it says. If sets A1, A2, dot, 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 A sub k contain n1, n2, dot, 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 n sub k elements respectively, right? There are, and this is kind of the formula, so maybe I'll even write this in a different color, but there are n1 times n2 times dot 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 times n sub k ways of choosing one element, so let's say an element from A1, an element from A2, dot, 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 and finally an element from A sub k. All right, and there it is in all its glory, this fundamental counting principle. Sometimes I just call it the multiplication rule, because that's all you end up doing right here. And kind of visually what it is, let's say you have these sets. Now, I'm going to draw these as rectangles, right? So not necessarily the same way we use the rectangle to denote things in a Venn diagram, but it could possibly be that, and let's say this is A1, this is A2, this is A sub k, and we have n1 elements here, right? And then n2 elements there, all the way up to n sub k elements here. And what you're doing, you can think of it either as a game, as an experiment. You're choosing any of the n1 elements first, and choosing any of the n2 elements second, and then finally any of the n sub k elements last, and you're trying to figure out how many ways can you do that, right? So essentially you have n1 choices for the first element, n2 for the second, and so forth, and k for the last. And then the principle is to see the total number of ways that you can make that choice, right? Or complete the choice from each of the sets, is to multiply all the n's together. So n1 times n2 times nk, right? Let's look at a couple examples. So, and let's look at number 1. So you have so what I'll do is I'll just kind of summarize the facts. So here you have a student organization, right, with 30 members, right? So they're all different, right? 30 members. How many ways? So here's our question. How many ways can you choose a president and vice president of this organization? So just no other criteria, you just have to choose a president and a vice president. How many ways can you do that? All right. So think about it this way. You're going to put the 30 names in a hat, right? So you're going to have 30 pieces of paper. Their names are going to be on it, and you're just going to pull one. And let's say the first name that you pull, they're going to be president. And then you pull another. The second name that you pull, they're going to be a vice president. So let's define A1 in this case. So let A1 be the set of possible presidents, right? Presidents. And then A2, similarly, the set of possible vice presidents. So then let's see if we can figure out how many elements are in A1, and then similarly how many elements are in A2. Well, to start, again, think of it, you have those 30 names in a hat, and you're just going to pull one at random. So there are 30 possible vice presidents. I'm sorry, presidents that could lead this organization. Now let's think about the number of possible vice presidents. Well, after you've selected the president, that president isn't going to serve as vice president as well, right? The president and vice president are going to be different individuals. So whoever you end up choosing as your president, that leaves a total of 29 to serve as a vice president. So then what's the total number of choices you can make? So the total number of ways, right? So the total number of ways is using our principle n1 times n2. So that is going to be 30 times 29. You guys could do your mental arithmetic. What do you come up with? Yes, I'm sure someone out there said 870. So yes, 30 times 29. That's 870 ways that you could have a vice president and a president chosen from a student organization with 30 members. And because this fundamental principle involves multiplication, it doesn't take, that many multiplications for numbers to get pretty big. So sometimes you end up with, the total number of ways of choosing something, and you're like, man, is it really that many ways? And yes, it is. Sometimes the numbers, the individual factors seem small, and as soon as you start multiplying, obviously, the relative magnitude increases quite a bit. All right. So that's one example. Let's look at another example. Let me describe this scenario. So there is a test, and this test is comprised of 12 true-false questions, right? So that's your test. So there's a test that has 12 questions, but they're true, false. The question is now, how many ways, right? So how many ways can a student complete this test? Right, so if for instance you are an instructor and you're trying to figure out, all right, man, how many ways can they actually do this? Let me fix my y. How many complete this test? And you want to know how many possible ways, how many possible exams could you end up grading, right? Let's see here. So it's basically, so what I will say is that, so A1 is the response on question 1 on this 12 question test, and then A2 will be whatever the response is, or the response on question 2. And then since there are 12 of them, I'm not going to write it literally. I'm just going to say, okay, yeah, and then that pattern continues. So A12 in this case is the response on question 12. So then how many possible responses are there for question 1, question 2, ... question 12? Well, because the test is a true-false, right, there are only 2 possible responses for each question, right? It's either true or false on question 1, true or false on question 2, ... true or false on question 12. So then the total number of ways that a student can complete this test, right? So in this case, the total number of ways, in this case, it's n1 times n2 times ... times n12. But in this case, because the number of elements, or in this case responses to each question, is 2, this will be 2 times times ... times 2, 12 factors here. So there are 12 factors there, and then that means our final answer is 2 to the 12, right? So I believe that is 4,096 ways that this 12 question test can be completed. Again, it's 12 questions, it's only true, false, but look at that. You end up with over 4,000 possible ways that this test can be completed, right? So that gives you an idea of how you can utilize this fundamental counting principle, right? Now, there are a couple other principles that are very, very useful as far as counting. And first, what I'm going to do is define what we call a permutation, and then give you a formula for computing the number of permutations in a given scenario, right? So we're going to have a definition and then a theorem. So if our objects are chosen from a set of n distinct objects, and then so what this immediately implies is that n is greater than or equal to r, right? So you're choosing r objects out of n objects, and then we're going to define what a permutation is. So any particular arrangement, let's fix that. So arrangement of these objects is called a permutation, right? So is called a permutation. Right, so the word permutation and the word arrangement can be used kind of interchangeably, right? So to give you an idea, let's say, let's say your universe here would be the digits 1, 2, 3, 4, 5, 6. Let's just say 7. And what you are trying to do is, so you're allowed to use these 7 digits and then create like a locker combination. And let's say this particular locker combination for a combination lock is comprised of 4 digits. So in this case, right, so we're going to create essentially what we're going to look at now are well, we're not going to list them all because there's so many of them, but in principle, all 4-digit arrangements, so all 4-digit arrangements from our universal set, right? So from U. So in this case, my N is 7, and my R is 4. So I'm just going to give you a couple examples of, again, this whole idea. These, let me write this properly. I don't know why my M's not showing up right. So arrangements, right? So here's one possibility. Yeah, you could have something like a combination 1, 2, 3, 4. That's one arrangement. Another arrangement or permutation, 4-digit arrangement or permutation from this universal set would be 1, 3, 4, 2. Even though your locker combination is 1, 2, 3, 4, not a safe combination anyway, and then someone else uses the combination 1, 3, 4, 2, even though the same digits are being used, it's a different arrangement of those 4 digits. That's why it's a permutation, right? So another one that utilizes the same 4 digits would be, maybe someone did it in reverse, 4, 3, 2, 1, etc., right? So again, the whole idea of a permutation is that order matters, right? And again, probably the simplest way to think about it is, to think about your combination or on a combination lock. Think about the pin for your ATM card, or think about the pin on your to unlock your device if you use the digits, whether it's a 4-digit pin or a 6-digit pin. Some software, some operating systems, that software now allows for a 6-digit code, right? And obviously the longer the code, then in principle the more secure it will be, right? So that's the definition of a permutation. So now the question is, how many possible permutations are there if I'm choosing R objects out of N distinct objects? So here is the formula. So the number of permutations of R objects selected from a set of N objects, again distinct objects, so from a set of N distinct objects is, and so here is the notation that we're going to use. So we're going to have N distinct objects, and we're going to permute a big P R of them, right? So there's a little n in front of the P and then a little R after it, so it's denoted this way. And it turns out this is the formula. It's n times n minus 1 times n minus 2 times dot 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 times n minus R plus 1, right? So when you start looking at the first few factors here, it looks like a factorial in general, but it doesn't necessarily go all the way down to 1. Sometimes it does, right? But not if n is equal to R, so you're permuting all the elements, you would end up getting a true factorial, but it doesn't always have to be equal. It doesn't always work out to be a factorial that you might be thinking of. But there's a way you can actually turn it into a factorial by doing this. Take this expression and so this is the formula so far, and then what I'm going to do is I'm going to continue subtracting 1. So then I'm going to end up with n minus r, n minus r minus 1, and then n minus r minus 2, all the way down to 1. So what I'm doing is I'm putting in these extra factors here. So I'm multiplying by those factors. Let's also divide by. So to make it equal, I can't just multiply by these additional factors. I have to balance it out by putting the same factors like here, minus 1, minus 2, all the way down to 1. So the things in red, they actually cancel each other out. So the first expression here is exactly the same as this, but why did I put that in? If you look carefully now, the numerator, it starts at n, and you continue to subtract 1 and multiply all those factors until you get down to the number 1. So the numerator is actually n factorial, and the bottom is something similar, but instead of starting at n, you're starting at n minus r, and then you're continually subtracting 1, and then you continue that process until you get to the number 1. So that denominator is n minus r, factorial. And this is the commonly used formula for the number of permutations of R objects from n distinct objects, right? So now let's do just a couple examples, and then that will wrap this up. So let's do that question that we did earlier. So remember when we were making our 4-digit codes, right? So how many 4-digit codes are possible, right? From the digits 1 through 7, right? That's essentially what we were doing there. Previously we had 7 digits, and then we were creating all these different codes. So in this case, n is 7 and r is 4. So to answer this question, what we need to compute is 7p4, right? And using this formula, as long as you remember your factorial calculation, so you have 7 factorial over 7 minus 4 factorial. So that's so now again, I encourage you to check out your graphing calculator to see what exactly you have to do in order to compute your factorial. But a lot of calculators, they do have the factorial function built in. You might be under something like probability. Some calculators have that, but your 7 factorial is 5040. And then at the bottom here, this is 3 factorial. Now 3 factorial is small enough that you can compute it mentally. It's 3 times 2 times 1, so that's 6. So then if I do my 540 divided by 6, I'm going to end up with 840. So what this tells me, if your combination can allows for digits 1 through 7, and you have to use 4 digits in your code, there are 840 different combinations you can make. So that means if this is a high school that has more than 840 students, and each student gets their own locker and has to create their own code, if you have more than 840 students, that means at least there will be at least 2 people in that school that will share the same combination. So not very safe, right? So maybe going 0 through 9 would be a lot better. So instead of having to choose from just 7 digits, maybe 10 digits will make it a lot safer. And in fact, that is the case. So I'll leave it for you to do something like, so like on your own, just try to compute 10p, still 4, and see how that compares to this number, to see how many more possible codes can be formed, right? So let's do another example here. And so let's do this. Okay, so here's our scenario. We have 9 cars in a race, right? How many ways can they place first, second, and third, right? So how many ways can they place first, second, and third, right? Well, here the order does matter, right? Because let's say you have car. So let's say you have it's cars 1 through 9, right? If they come in this way, let's say car 5 and then 8 and then 1, right? If that's 1 first, second, third, well, that's different from having C1, C8, C5. That's a different first place winner, second place winner, third place winner. So again, this is a situation where order matters. Similar to choosing your vice president and president, right? So how many ways can this happen? Well, in this case, the N is 9 because there are 9 cars in the race. And what you're trying to do is to figure out how many ways you can order them in first, second, or third. So those are 3 slots to be filled. So your R is 3. So we end up with 9 P3. So we have 9 factorial divided by 9 minus 3 factorial. So what's 9 factorial? Well, we know that's going to be a little bit bigger. I'll let you, give you a second. You can pause the video and try to compute it, but it is quite a big number, 362,880. And then at the bottom here, 9 minus 3, so that's 6 factorial. What is 6 factorial? Again, see, that's 720. So if we take 9 factorial divided by 6 factorial, we end up with 504. So again, in a race with only 9 cars, there are 504 different ways that we can have a first, second, and third place winner. So again, pretty remarkable, and it has a lot to do with just, multiplication, right? We know that factorials are multiplication, and the factorials just give us an easy way to represent this formula for a permutation. But multiplying all those factors out tends to lead to numbers that intuitively you wouldn't really think, man, there are that many ways that this can happen, right? So there's one other counting technique that we have to look at, and it is related to a permutation with just a slightly different definition, and we will take a look at that in a successive video. So see you then.